Everyone, Mary here, and we're going to talk a little bit about thermodynamics. Now, thermodynamics is a huge topic. It's got a lot of math associated with it, and that's not the purpose of this class. We are going to give just a big overview of the basic rules, so you've heard of it and you can use them, but we're not going to go deep into the math. And why? Time. We don't have the time to do all the lovely physics I wish we could do. So what does thermodynamics mean? Well, thermo means heat, like thermos bottle or thermometer. Dynamics is why things move. So thermodynamics is the how and the why heat moves and does work. And when we say work, we mean the physics definition of work: apply a force through a distance and actually move an object. The first law of thermodynamics is a restatement of the law of conservation of energy to include heat. And actually, James Prescott Joule showed that this is true. The first law of thermodynamics basically says that the energy before something happens equals the energy after something happens if you account for all the individual pieces of energy before and after. Now, when we're talking about a heat system, we also have to talk about the changes in heat within the system. And so a classic example of that is an internal combustion engine. So if you have a piston that has an explosion, some gasoline explodes inside of a piston, and that does some work and it moves a cylinder to compress some more gases and compress some more gases and combust those, the whole thing is going to get a little bit hotter, and some of the parts are going to move, meaning a force is going to be applied through a distance. If you account for both of these, the change in temperature and the change in motion, change in work that is done, they will equal the amount of energy that is input into the system. So, law of conservation of energy, just including heat, that's that first law of thermodynamics. Most of this video we're going to spend on the second law of thermodynamics. Second law of thermodynamics is a pretty wacky one, and it can be interpreted in a couple different ways. So we're going to start here. Second law of thermodynamics says this: heat always spontaneously flows from high temperatures to lower temperatures, never in the reverse direction. So here's what I mean. You've got a hot cup of water sitting on your kitchen counter. The water is 100 degrees Celsius. Your room is 21 degrees Celsius, which is about 68 Fahrenheit. If you leave it sit there, what will happen is the water is going to get colder and the room is going to get hotter. Heat always flows from high concentrations into cold concentrations, never the other way around. Never are you going to have the water getting hotter and hotter and hotter and really super duper boil dry sitting on your kitchen counter, and have your kitchen get to a point where it's now like 10 degrees Celsius. That's just not going to happen, and the reason is because of the second law of thermodynamics. Here's another example. Let's say I had a fish tank, and in the fish tank I had a barrier between one side and the other. If one side contained cold water, the other side contained hot water. If I removed the barrier, what am I going to get after everything mixed? I am going to get a nice big tank of warm water. That's always going to happen. The heat is going to be given to the cold, and never vice versa, where this is going to get hotter and that's going to get colder. Now, another way of interpreting the second law of thermodynamics is to say that 100% of the energy of a mechanical system, meaning a machine, cannot be transferred from one object to another due to the spontaneous flow of heat from hot to cold. Some energy will always leave the system whenever work is done. A force is applied through a distance. Let me give you an example of a simple household fan. So let's say you put 100 joules of energy through the electrical cord into this fan. Well, a lot of electric motors are about 95% efficient. So let's say 95% of the energy goes into moving the fan blades and making the fan run. But 5 joules are lost to heat, parts of the fan, internal friction parts inside the actual motor itself. Because this is going to have moving parts there is going to be some friction. If there's going to be some friction, there's going to be some heat. And where does heat go? From high concentrations to lower concentrations, it is always going to dribble away. You will always lose some energy. Automobiles. Automobiles are about internal gasoline engines, about 25% efficient. So you put in 1 gallon of gasoline, about 25% of it makes the car go. 75% makes heat. It makes the engine compartment warmer. It makes the air around the car warmer due to air friction. And what happens? That heat flows away from the car. It just dribbles out and makes the highway and the air around it a little bit warmer. Same thing happens with the human body. Muscles are, again, about 25% efficient. You eat food, about 25% of it makes your little muscles move so you can move and operate, and 75% of it you dissipate off as heat. When you snuggle your sweetie pie, it makes you nice and warm to cuddle, but that is going to turn into heat that just heats the air around you and your clothing, etc. This law prevents perpetual motion machines from existing. Please don't invest your money in a perpetual motion machine, because a machine is something that can do work, exert a force through a distance, and there has to be motion. Well, if there's moving parts, there's going to be friction. If there's friction, there's going to be heat. If there's heat, it's going to leave. It's going to dribble away into the surroundings. And the heat that dribbles away into the surroundings is going to steal the energy from the machine. And no matter what kind of machine you start with, it will eventually stop. It will not move forever because of the second law of thermodynamics. Another way of interpreting this second law is it's sometimes called the law of entropy. Entropy is defined as the disorder or the randomness of a system. And the second law states that heat always flows in the direction to increase entropy. Let me give you an example. Let's say I have my fish tank, and my fish tank, again, has a divider in it, and I have a cold side and a hot side. I take the divider out, and I end up with a very large tub of warm water. Now you might say, wait a minute, you're saying this is more random than the above, but everything here is the same. Sameness is not very useful when it comes to energy. If all the energy is the same, no work can be done. Let's say in my little barrier between my hot and my cold side of my fish tank, I had a little fan. And as the water moved from the hot to the cold, or the heat moved from the hot to the cold, it could cause this little fan to rotate or move. It could do that as long as there was water flowing in this direction. When that water stopped flowing, the fan would stop moving. You have to have different quantities of heat energy in order for a system to do work. Now, entropy always increases. This is a statistical law based on probabilities and calculations. It's pretty advanced math. And what it says is the most probable outcome in any situation is the one that increases entropy. So if I have a cup and I drop it and it smashes to smithereens, this is increasing entropy. Here, all the molecules are very organized. Here, the molecules are not organized. This is high entropy. This is a lower amount of entropy. And this law says that the cup is going to break when it hits the ground. But the wacky thing about this is because it is a calculated probability, there is a highly improbable chance, but not an impossible chance, that each one of these little pieces could spontaneously jump back together and reform the cup. Would you bet the farm on it? I wouldn't bet the farm on it. But is it possible? Yeah, it's possible, but highly improbable. Entropy is how we measure time. We measure time by occurrences. The sun goes up, the sun goes down. We measure time by the flow of energy, and our star constantly emitting energy as we go around the sun and the moon goes around us. But That is called the arrow of time, and time itself always flows in the direction of increased entropy. If you want to have a deep philosophical discussion with somebody sometime, talk about this and how it relates to time travel. The third law of thermodynamics is the law that says a system will become zero. The entropy of a system is going to become zero when its temperature reaches absolute zero. So what does that mean? Let's say I've got one big puddle of energy, like I've got the sun sitting in the middle of our solar system. As long as it is there, pumping energy out and giving it to things like our planet so that trees can grow and grass can grow and critters can eat the grass and you and I can eat grass and critters, then life can happen and the world is exciting. When all of the energy is smeared out, like all the butter gets smeared all across the bread, so it's all the same, then nothing can happen. We would have no life on the planet, we'd get no motion, no work could be done, and the world and universe would be a very dead place. That's referred to as the heat-death hypothesis. This was hypothesized many hundreds of years ago, that if everything in the universe became one temperature, then we would have no motion, no work could be done, and nothing would move. If our current universe continues to expand forever and ever and ever, the energy within it will keep spreading out like the butter spreads out on that bread, so it's the same everywhere. And then the universe will die in a whimper, not in a bang. This is a baby picture of the early universe. This is called the Planck map, created by the European space agencies. And each one of these little red spots is a hot spot in the early universe that led to a galaxy. Pretty cool stuff. The third law of thermodynamics says that we will never get to absolute zero. Because heat flows from hot to cold, to get to absolute zero, you must provide a location colder than absolute zero for the heat to flow to. And that doesn't exist. So we can't get to absolute zero. Now, there are some recent experiments where some people say that they have, but it has to do with some quantum physics and some wacky math. So stay tuned. Never say never in science. We've got the first, second, and third law of thermodynamics, but after they created all three of those, physicists realized they needed one more law, and they called it the zeroth law. And this one had to be put in front of the other three. And this is what this law says. If two systems are each in thermal equilibrium with a third system, then the two systems are in equilibrium with each other. Basically what it says is this. If I put a glass thermometer in hot water, and if the glass thermometer and the hot water are the same temperature, and the alcohol and the glass are the same temperature, that means that the alcohol can tell me the temperature of the water. It basically says if this equals this and this equals that, then this equals that. It's a small little thing, but that law had to be there before we could do thermodynamics. So a really quick overview. The zeroth law basically says thermometers work. The first law, you can't get something for nothing. That's that conservation of energy. Second law says you can't even break even. Heat will always leave the system. And the third law says once you get to absolute zero, nothing's going to move. All right, that is a fast and furious overview of thermodynamics, and we will see you another time. Bye-bye.